Hello everyone, welcome to Tactica Imperialis and to today's video. Today is the first episode of Tactica Tutorialis, my new science series that I started off with a little introduction a couple of weeks ago, and now we're ready to begin. So, today I'm not going to do the most requested topic because that's the bolt gun, and I'm not touching the bolt gun for a bit because the bolt gun is a complicated nightmare fuel. So what I'm going to do instead is something even more annoying, but has better physical applications. And what we're going to talk about today is probably the second most iconic weapon in Warhammer 40,000, I think. We're going to talk about the Lasgun. Now, this is going to be a really long video. I've already done one take of this, and it took me 40 minutes to get through everything I wanted to do with the Lasgun. I'm not going to try and do it in 40 minutes again. I'm going to try and do it faster, but there's a lot to cover here. So I'm not only going to do one video, it's going to be on the Lasgun, one topic. But that's broken down into three subsections. Now, section 1 is a bit of background, so lasers. We're going to do very quickly how lasers work. That's going to be part 1 of this lesson. Part 2, we're going to talk about damage. We're going to talk about how lasers deal damage and then specifically apply that to the Lasgun, because we need to know how the Lasgun deals damage so that we know how our Lasgun works. Part 3 is a bit of a fun thing that I wanted to talk about, sort of as an extension, and I want to talk about power. I don't mean by power as in the power of a shot, though I also kind of do. I mean how much energy is stored in a Lasgun that is used to power the gun. How much energy is needed to power a Lasgun in full, and how much does that actually represent in our world? It's a bit of a fun addition that I wanted to show off, so I'll get to that at the end. But we have 2 big topics to cover, and these are the main bits of fun. So, first I'm going to break down how lasers work, then we're going to break down how they deal damage, and then we'll have a quick look at power at the end. If you want to treat it like an actual lesson or a lecture, feel free to make some notes. It might help you if you want to plug some numbers in, do some calculus, look some stuff up. Might be kind of fun. So, let us begin Tactica Tutorialis. Also, thank you very much to the artist who created the intro that you've just seen. Link in the description if you want to check that out. And so, let us begin. Okay, part 1 of this lesson, lasers. We need to understand at a basic level how lasers work, because I think that's important, because it's all well and good saying, oh, we have a gun and we push a trigger, we get some light. How? You want to know how. We're scientists. This is what we do. So, first concept you're going to need to understand with lasers, and I'm apologising that I'm giving you quantum mechanics in the first 90 seconds, is quantum mechanics. The main fundamental principle we need to know for lasers is quantization of energy. And yes, I will spell it with an S, not a Z. I'm British, therefore I used S, not a Z. Quantization of energy. What that means in layman's terms is that energy is not continuous. You can only have certain intervals of energy, and we call those energy levels. The way we represent this is through a simple diagram of levels, so 1 and 2. For our laser, we usually use a 2-level system where we have state 1 and state 2. State 1 is our baseline. This is our ground state. This is where most of our atoms live 99% of the time. State 2 is the excited state. This is a state where particles can jump to if they get enough energy. This is where the quantization comes in. You must give them the right amount of energy to allow them to jump to level 2. And when they get there, they don't usually stay because it's an unstable state and they jump back down to level 1. But they do that by getting rid of their energy, and we call that de-excitation, and that usually causes the energy to be released somehow. If you want a really good example of this, look at fluorescent light bulbs, because they use this exact principle. A fluorescent light bulb is just de-excitation releasing light, releasing photons. We call it fluorescence. And that's the basic principle of lasers as well. So, what we have is we pump our atoms into level 2. We force them to go and live in level 2 for a bit, and then we let them come down. I'll draw this with another colour. They come back down, like so. However, while doing so, they have to get rid of this energy gap. They have to deal with this and get rid of that energy, which means they have to release it. They can't destroy it, so they have to release it. So we get a photon is released, and we call that spontaneous emission. So at random, atom drops, releases a photon. Fine, that's lovely. But with a laser, we use something called not spontaneous, but stimulated emission. Stimulated emission. We use this stimulated emission as follows. So, as our atom is on its way down, what we do is we supply it with another photon. Oh, wrong end. And we pick that photon's wavelength very carefully so that it is equivalent to this energy gap, because there's a formula that links energy to wavelength, and we'll get to it later. And what that means is that instead of one photon being released by our emission, we get 2. 1 and 2. And these 2 photons are identical to the one that we put in. And these can then go and do this process all over again, which means that we multiply the number of photons that we have in our system. In fact, laser, I've stood in front of it, laser is an acronym. And it talks about the light amplification by the stimulated emission of radiation. So, by doing this process, this stimulated emission of the radiation, which is this light being released, we amplify and increase the amount of light, and therefore the amount of energy that we get in our overall beam. This is the basic principle of lasers, and we use this all the time. This is the fundamental of how our Lasgun should work. You can have more complicated lasers than this, with multiple tiers of levels that are fast and slow and all sorts of nonsense, to be honest. You can have very complicated laser systems, but this is the basic principle. Stimulated emission causing more emission and light amplification. That's it. That is it. If you take nothing else away about lasers, remember that word, or those 2 words, and that diagram. If you can remember that, that's the important bit. Now, we're all briefed on lasers. This is how they work. But now let's talk about the Lasgun specifically, and that means it's time to talk about damage. So, damage. How do Lasguns deal damage? Well, we need to call upon our knowledge of Warhammer 40,000 for this, and the way that the wikis and the Imperial Guard, I believe the 3rd edition codex described it, is that Lasguns do damage via heat. So what they do is they heat the immediate surface area that is that's hit by the beam. I wish I had a laser pointer so I could do this. That area is illuminated, it is heated, and it is vaporized with that little pop. That is the basic principle of how a Lasgun works. So what we have is light turning into heat, leading to vaporization. And I will write it with a U just to be annoying to the Americans. I am sorry. That is the process of how a Lasgun works. In short, you want it in one word, one sentence: light converted to heat on contact, leading to vaporization of the target. That's it. Now, how does it do it? Well, this is what we call a photothermal reaction. We have a photon causing a thermal energy change, a temperature change, and that causes our vaporization. So photothermal. Starts to make sense when you actually understand the root words. So that's what's going on. The trick here is actually being able to know how much energy we need in our Lasgun. And for that, we need to start making some assumptions. And this is the problem with physics. We have to make a lot of assumptions and they get very, very annoying. So, first thing we need to know is how much energy our photon has got. So we're going to use one photon as our example. And the first thing we need is our energy. So the energy of a photon is equivalent to hc over lambda. I hope you can see that. Yeah, I think you can. Is hc over lambda. I apologize if it's a little bit small on the screen right now, but I'm just going to have to work with it because this is how much blackboard I got. I might, if I get time, buy a bigger whiteboard and then we can have some more fun. So, hc over lambda. Constant, wavelength. Don't need to worry about these constants, they're just numbers. This is the wavelength. This is the important one. The second formula for energy we need to know is K little b T. You might have seen this without the little b. I write it with a B. This is Boltzmann's constant. It's just a number. You don't need to worry about it. And this is temperature. And this is energy. It's a very badly written E, so I'm going to rewrite it. That's energy. That's temperature. That's a constant. So we have three things that vary. Temperature, wavelength, and energy. And the trick is we need to equate these two things. Because the energy of our photon, as we said here, I rubbed it off, is the light from our photon is being converted into heat. So that light energy of our photon, if you like, that photon's energy is being converted into thermal energy. So we equate the two. So we say, go back over here now, that hc over lambda equals kBT. I have not accounted for efficiency here. I have assumed 100% efficiency, which is rubbish. That never happens. In fact, let's be a bit harsher. Let's put 10% efficiency, so 0.1. Let's say that our Lasgun is 10% efficient at transferring its photon's energy into heat. That's probably very optimistic biologically, but we're going to go 10% anyway. Let's try that. Now, this is where the second assumption comes in. You can do this in one of two ways. You can say, what is the energy I need to vaporize X? And X in our case is water, because we're mainly targeting cells. Cells normally contain water, so we plug in the temperature needed to boil water, which is 100 degrees C, though you would use Kelvin, because this is physics, we use Kelvin. So it's basically add 273 to whatever number you're aiming for, just stick that in. Plug that in there, rearrange the equation a bit, and solve for lambda. That will tell you the wavelength you need for one photon to vaporize one cell of water. Give or take. That should tell you, obviously there's a bit more to it than that, but roughly that's about right. I've not got into specific heat capacity. In fact, I probably should have done a different equation here. I probably should have used mc delta T and then used a temperature change, mc delta T. I said, how much energy do I need to provide to change the mass of my water content by a certain amount of energy? So that's another way you can do it, and probably that's going to give you a more accurate amount of how much you need to boil your water or to heat up and destroy your bones or whatever else you're aiming to do. That's probably a better formula. However, what's more interesting is to try and take the Lasgun and make it work, and that means we need to pick our lambda. Now, most Lasguns have, in typical representation, red beams. I think I'm about right in saying that. We usually have red beams. So, we need to pick a wavelength of red light. Now, conveniently, we know that. You can look up any electromagnetic spectrum you like, and you will find that the wavelength of red light is approximately 700 nanometers, which is tiny and insignificant to you because you don't know what a nanometer looks like. If you like, it is 700 millionths of a millimeter. That's how small that is. But that's its wavelength of our light, which is an electromagnetic wave. I'm not going to get into all the details, the basic principles of light and energy. We will be here all week. We plug that in, and we solve for delta T, and the amount of temperature that we can get into our cell is pretty crazy, because cells are very light, they're very, very small, so you've only probably got maybe half a gram of water, a gram of water. You don't have a lot of water. And whilst you need a lot of energy to heat water up, 4,200 joules per Kelvin per kilogram, when you've got such a small mass of water, your energy change, your temperature change, is going to be absolutely bananas. Excuse me. So that means that we can very easily vaporize our cell. If you use the kBT formula that we have up here, I did the math, and you get about 2,000 Kelvin in terms of the amount of, if you convert, you do H over lambda equals kBT with the 0.1, you get 2,000 Kelvin. That's the amount of temperature that is equivalent to the heat that is transferred. It's a huge number. I haven't actually stuck this number in. You can stick this number in at home if you like, if you've got a calculator in front of you. Stick it in, think about the water content of a cell, guess a mass, look at the specific heat capacity, give me a temperature change, let me know in the comments what number you get to see if you could, what you can vaporize with that. If you get to 100 degrees from body temperature, then you vaporized water, pop goes the cell. You can also look at it with bone to see if you can cut through bone using this. That's just another interesting application. But that's only half the story. So we talked about now how the laser actually does the damage. But that's one photon to one cell. We have a lot of cell to cut through. We have a lot of body to cut through. And that means we need to talk about absorption. So, when light hits stuff, it is either absorbed, reflected, or transmitted. It's a bit of an art form, if you like. Absorption, reflection, transmission. I've just made that up on the spot. Light interactions is art. Absorbed, reflected, transmitted. Now, this is how colours work, by the way. Reflection back into us is why we see certain colours, and absorption means we don't see the other colours, which is why we see the ones we think we do. Won't get into that here. But when light passes through a medium, it is absorbed. Always. Pretty much. And the formula for this is linked to the intensity. I'm going to leave that formula up. And it is linked to intensity. And it is what we call an exponential decay. So what that looks like in maths is this. Excuse me. So the intensity of our beam at a distance x, I'm going to work in one dimension because it's easier, is the equivalent to our initial intensity, which is the initial power density of our beam, multiplied by an exponential factor where x is distance into the surface, and mu is the absorption coefficient. This is the probability that a photon is absorbed at any given distance. And this number is horrible. Picking this number is impossible because it varies like billiard. It varies with wavelength and it varies with material. So if we were to say take my leg, I wanted to shoot a lasgun bolt and try to see could it cut through my leg. For example, I have got skin, muscle, bone, blood, water, and goodness knows what else going around my legs right now, and I need to work out how absorbent all of those materials are to the wavelength of my lasgun light. And I don't have the will and the strength and the data to work that out. So we're going to just pick a number. And the number we're going to pick as a rough average is 0.2. It could be anywhere between 0.1 and 0.5, probably. You could maybe find the data. Okay, I'm going to get a drink. I'll be back in a minute. So yeah, mu is a pain. Picking a value for mu, I've gone with 0.2. Your mileage will vary. Maybe you can find a way to do a weighted mean. I'm not going to bother. I've also added here 18 centimeters for our distance. That is the diameter, the length of my leg, basically, because we're using my leg as the example. You again, the number you stick in here, it varies. you'll get a slightly variable on your intensity. Now, the intensity of our laser, I'm actually going to use a modern contemporary laser. So a lot of lasers we use for photothermal interactions, because again, light to heat, photothermal, the maximum intensity that they have, there are ones with higher, but the highest intensity we use for those is I0 equals 10 to the power of 6 watts per centimeter squared. That is what we call standard form. It's 10 to the power of 6 is 10 by 10 by 10 by 10 by 10 by 10. So that's how that works. You'll see powers a lot when I write stuff down. There's another one here with a squared. So get used to seeing that. So that is the most powerful photothermal lasers we have these days. And when you stick these numbers in, 10 to the 6, 18, 0.2, you get a final intensity that comes out at, what was it? Actually, I've forgotten to do something. I'm really sorry, this cough is killing me. Right. That's in centimeters squared. We can use a beam of 1 centimeter square if we want to. Again, you can vary that to millimeters squared. In fact, I will put it in millimeters squared if you want. So it depends on how big you think your beam should be. Maybe get a ruler, use a laser pointer, work it out. We stick that number in, and we get about 2,700 as our final intensity. That leads to I of X equals approximately 2,700. Now that's a lot. That means that there's enough power in that lasgun, in that laser, assuming this number is right, to cut through my leg no problem. And since we have the photons in it all at the same energy, because it's a laser, they're all the same wavelength, therefore they're all the same energy, that is absolutely grand. So a lasgun could easily cut through somebody's leg? Yes. Could it kill somebody? Yes. Photothermal lasers are dangerous, and we use them for ablation and stuff like that all the time. So lasguns scientifically are actually quite sound. So if you want to take away from the video, if we could build one that was compact enough, we could actually make it work. But now I want to have that little discussion at the end about power. How much power, or I should be more accurate, how much energy can we store in a lasgun? So, when we're talking about power, we're also talking about energy, because the two are very much interconnected, and I don't like using the word power, but I can't think of a better word for it. I should probably talk about like energy storage and then converting it into... Anyway, what we're going to talk about is how much energy is stored inside the solar cell of a lasgun, because that's an interesting little study in and of itself. So, first thing we need to know is our intensity, and we need to convert that into an energy. So, as we already had our I0 from a minute ago of 10 to the 6 watts per centimeter squared. That's lovely, but that means nothing. So we need to work out how to get this into energy, or an energy density that we can then convert into energy. So the first thing we need to do is watts to joules. Now the formula for that is power equals energy over time. So we need to work out, I think, the exposure time and how long our pulse takes to transmit all of its energy into our cells. And I'm going to be very arbitrary, and I'm going to pick a time of half a second. You might think that's generous, you might think that's harsh on the lasgun for how long it needs to transfer its energy. You might think it needs a second, you might think it needs 0.1 seconds. We're going to pick 0.5, we have to be a little bit arbitrary because we don't have a lasgun to check. So we put that number in, and we get equals 2 times, so energy density, 2 times 10 to the 6 joules per centimetre squared. Now we need to deal with a centimetre squared, our surface area of our exposed skin or cells. And to do that, we need to know how wide our beam is. Now, I already asked you to have to think about this already. How big do you think it should be? We're going to keep to 1 centimetre squared for the sake of argument here. We're going to say that it is 1 centimetre by 1 centimetre in a square. But obviously, have a think about what you think the area of the impact zone for a lasgun beam might be. You might think about doing it as a circle and doing pi r squared. You might think of keeping it as a square and picking a different length, or whatever else. Pick a number and a style, and maybe justify it in the comments, and we can have a discussion about what seems realistic. But I'm going to keep it a 1 centimeter square just for the sake of ease. So if I use SA, surface area, equals 1 centimeter square, that leaves us with an energy of 2 megajoules, where mega is 10 to the 6th. They mean the same thing. This is just letter notation, this is number notation. I will use both a lot during these lectures, so learn to deal with it, I guess. Like kilo, mega, giga, micro, milli, nano, so on. That'll come up a lot. That's the connection. It's just 10 to the 3 variables. So we have 2 megajoules of energy-ish. And that is in one pulse from our lasgun. That's one pull of the trigger is 2 megajoules. But looking at the data from the codex again, we roughly think that it is about 150 shots in a lasgun. 80 in a las pistol, 150 in a lasgun. I'm getting that from Lexicanum, that they do have a source for that. So we're going to multiply that by 150. Because we have 150 shots per cell. And that is per shot. Therefore, E total is this times this equals 300 megajoules. 300 megajoules. That's how much energy I think is stored in the cell of a lasgun. But what does that mean? 300 megajoules is just a number. It's a nice number. It's a big number. But what does it mean exactly? Well, what I'm going to do now is I'm going to convert it into kilowatt hours. And kilowatt hours is how we measure the energy that we consume in our homes. So, if I was to put this number in, you can put this in a converter if you like. In fact, I very recommend you do. You will get a number in the region of approximately 90 kilowatt hours, I think. The first time I did this, I did it for a las pistol on my notes. I did it with 80 shots, so I had 160 megajoules, and that gave me 44 ish. It gave me 44 for 160, so I probably aimed a little bit high. So you're probably looking at about, let's say 80. Let's say 80. Again, feel free to do this calculus on your own at home and stick some proper numbers in, and we'll have a discussion about it in the comments. But we've got about 80 kilowatt hours. That is roughly the amount of energy that our lasgun has got. Now here's the clincher. So, in the US, the average US home uses, in 2018, 800, and I looked this up, 867 kilowatt hours per month. 867 kilowatt hours per month. That is what the average US home uses. So think about that if you're an American. Obviously, you can look this up for your own home nation as well, exactly what they would use in an average month for a typical household, and divide it by 80. So for our American example, or divided by the number you get. For our American example, we get about 10, 11. That's how many lasgun cells are needed to power the average American home for a month. One lasgun cell, in theory, if these numbers are accurate, so if we use half a second as the exposure time, if we say it has a surface area of 1 centimeter squared, if we say all of that, and your numbers will vary depending on what numbers you think are accurate to stick in, one cell of a lasgun will last your house about 3 days. if used correctly. Now this again assumes 100% efficiency, which is rubbish. You don't get that. And I haven't considered here the optical pumping that is required to keep the lasers pumped up, which would increase the energy even more. So that number might be too small. But that's just a little bit of fun to think about just how much energy is required to power a lasgun. And that's all charged by the sun. I'm not going to get into solar cells here, but if you were to look at solar cells, you'd find that they're not very efficient right now. So the solar cell technology of the Imperium must be bananas level efficient to be able to charge a lasgun cell in a few hours to that much energy. It's bananas. But that is all for today. That is everything I think that I can teach you about the lasgun. That is how lasers work and how they deal damage. I'm not an engineer. I'm not going to tell you how to build one, because I can't, or I would have done. But that is the principles behind lasers and how they do damage via photothermal interactions. I really hope you've enjoyed this video. I realise it's quite long. It wasn't really what I intended Tutorialis to be, but I really wanted to give you a full in-depth lecture and discussion about the lasgun because it's such an iconic weapon and it's a good place to start the series. If you enjoyed it, let me know what you think in the comments below. Maybe tell me what numbers you used in your calculations and what that represents in terms of the data that I was using there. So compare that 867 to your data. How many Lasgun cells would you think you need? And think about all those different calculations we've done throughout the episode and let me know what you think. I'm always interested in getting some feedback. I might get a whiteboard next time so it's a bit easier to write on. Not quite sure. And leave your suggestions for future topics in the comments as well. For now though, thank you very much for watching. This has been Tactica Imperialis and this has been the first episode of Tactica Tutorialis. Hope you enjoyed it. Thank you very much and goodbye.